This is a 3-span continuous bridge, and here you can see the ironworker splicing 2 sections together on the ground. In order to make this splice, the girder must be supported in a no-load condition. That is to say, all of the dead load camber has to be taken out. And you can see these supports have been placed to a predetermined elevation so that the dead load deflection is removed. These members were originally assembled in the shop, also in a no-load condition, and in that unloaded condition with no dead load deflection, that's when the splice material was drilled. And that condition of no dead load deflection has to be reproduced here at the job site before the connecting material can be reinstalled. Here 2 iron workers are installing the high-strength bolts which make up this connection. The iron worker standing behind the girder is using an impact wrench, and from time to time these bolts should be checked with a calibrated torque wrench to make sure you're achieving the correct torque. Here 2 iron workers are installing the intermediate diaphragms, and they are wearing harnesses and they are tied off to prevent an accidental fall. I'm a little concerned about the ironworker on the left, who is actually leaning on his harness, and his safety line is taut, and he is depending on that for his support. I don't think that's the best practice. They could easily have put some timber planks down between the bottom flanges of the girders, and that would have been their primary support. The fall protection is their backup for an emergency. I don't think it's good practice to use that as your primary support. The ironworker on the right has waited until the diaphragm is pinned in place, and now he's come down and he can stand on it. His lifeline is slack, and I think that is the better way to do this. Here the last member of that continuous girder is being installed, and a spreader bar is being used. Instead of picking the girder at the midpoint, that load is being distributed in an attempt to also minimize the dead load deflection of that member. Now in the field, if you're trying to fit a piece of steel like this in between 2 previously erected pieces of steel, the chances of getting those holes aligned are very, very small. And typically the base plates supporting the steel are not in their fully welded final position. So there is an opportunity to have some movement there in order to align these holes and join these pieces. Only after they're joined should that supporting base plate be welded in place. Here's a detail of the stay-in-place forms, which are very often called pans. They are attached to the structural members by tack welding, and you can see some of the welding here. Now in the tension area of the flange, you are not permitted to weld along the edge of the flange, and these straps have to be introduced, and you're actually welding to the strap. Here 2 straps are overlapped in order to get the correct width, and no welds are taking place on the structural member. The welds are done on these straps. Here is a detail of the installation of the shear connectors. This round shape is a ceramic ferrule. The ironworker inserts the stud or the shear connector inside this ferrule, brings it to the location where he wants to install it, and when he squeezes the trigger, an arc is generated that melts the surfaces and automatically plunges the stud into that molten pool, which is held in place by this ceramic ferrule. Afterwards, you need to break away the ferrule and dispose of it. That should be removed before you place the concrete. Now, there are many other hardware devices which take advantage of this technology and allow you to install them very, very quickly and effectively. After the metal pans are installed, you install the shear connectors. And here the inspector is striking each one to make sure there's a good connection. What I've also seen is some number of the shear connectors are actually bent over at right angles, which seems like a much more demanding test. She's getting very close to the ironworker who's installing the studs, and he's very unhappy about this, chases her away. After the steel is erected, a survey is made of the actual elevation of the steel over its full length, and that is compared to the theoretical elevation. You need to account for the dead load deflection which will take place when the concrete is placed, and you finally come up with a number, and it's written right down here as 0.062, which is about 3/4 of an inch. And this tells the installer that the formwork should be set, this permanent stay-in-place form should be set 3/4 of an inch higher than this reference point. And that will put the underside of the deck at exactly the right elevation. After the dead load takes place, the concrete will be in its final theoretical elevation. I wanted to show you the activity of placing the rebar for the deck. In the foreground, these white strips have been placed in the depressions in the corrugated metal form. They are strips of styrofoam. If you did not install those strips, you would be wasting a lot of concrete in filling the depressions, and at the same time that would simply be adding to the dead load on the bridge. So those spaces are filled out with styrofoam. Here the ironworkers are shaking out the steel. Everything here has to be done by hand. All the bars have to be carried to their locations and placed, and then all the bars are wired in place. placing the transverse bars for the top mat of steel, and the bars are supported on chairs. In this case they are continuous chairs, which will set them at the correct elevation.